So just a few words on now heterodiatomic molecular orbitals. So that means molecules with two atoms that have are different elements. Okay, so the MO diagram, for example, for carbon monoxide would be a heteronuclear diatomic, and things are going to look pretty similar. You're going to have the two s orbitals and the two p orbitals involved in bonding, but the energies now are different, right? Oxygen is more a greater atomic number, and so the ionization energies of oxygen are greater than carbon. So the atomic orbitals are more stabilized, right? We can go back here and look at that. All the oxygen lines are lower than the corresponding carbon lines. And so these are going to be the oxygen ones on this side, and these are going to be the carbon atomic orbitals on this side. And what ends up happening is you get the same sort of general shapes of the molecular orbitals, but because the oxygen atomic orbitals are lower in energy, the MO energies of the MO energies of the bonding orbitals are closer in energy to the oxygen atomic orbitals, and the energies of the antibonding molecular orbitals are closer in energy to the energy of the carbon molecular orbitals. This has implications for exactly where the electron density is. There's a principle that basically states that MOs that are closer to their AO's counterpart have more of that AO character. So if we were to draw these MOs out, and let me just do that, right? If we were to draw those AOs out, right, kind of the traditional way we draw it here, sorry, these MOs. So that's this MO right there. We would draw two s orbitals constructively interfering. But what I'm trying to say here is that because this s orbital is closer in energy to the oxygen AO, really a more accurate depiction of this molecular orbital is something like this, where you have a much greater electron density on the oxygen side as opposed to the carbon side. The opposite is going to be true for this. This is an anti-bonding MO. So it would look something like this, where you have a much larger atomic orbital. I drew this larger one on the carbon side because we're closer to the carbon atomic orbital from which the molecular orbital came. Same thing for example, let's draw one of these pi orbitals. It would look, this is pi anti-bonding. It would look like this. Okay, more electron density on the carbon. And then for this pi orbital here, one of them would look, this is going to be a bonding interaction. One of them would look like that, okay? Where the oxygen is going to have more electron density. So electrons going to spend more, the electrons in that molecular orbital, in this case, are going to spend more time in located near the oxygen atom as opposed to the carbon atom. I mean, that's what these depictions mean. And that can have profound implications for how the electrons in these molecular orbitals react. And later on in the course, will actually help us explain many different things about reaction activities and dynamics.